Today we're going to be taking a look at some really interesting precision peak detector circuits that not only have a much improved frequency response over the more traditional peak detector designs, but they also provide infinite persistence. And no, they don't do it using microcontrollers because, what fun would that be? So here's your basic standard peak detector circuit. You've got two op-amps, a diode, and a capacitor, and it's pretty straightforward. This op-amp is there just to overcome the forward bias of the diode, so you don't have errors due to the diode forward voltage bias, and it allows current to go in one direction and charge the capacitor. So when you have a positive input voltage, you charge this capacitor up to whatever that voltage is, because this is just a follower circuit, so its output is going to equal its input. However, when that voltage drops down, this capacitor can't discharge back through the diode, and this buffer here just prevents the capacitor from draining off too quickly. So if we have a very high impedance buffer here, the capacitor will keep its peak value for a reasonable amount of time. And at lower frequencies, you can see this works very well. I have a 1 kilohertz signal going into the peak detector circuit at 2 volts peak to peak, and it's tracking that peak voltage of 1 volt peak very nicely. However, as we start going up in frequency, we start seeing a little bit of error here. So if I roll this up to about 10 kilohertz here, you can see we've got about 1.5% error there. We're down to 985 volts on our peak detector output. Roll that up to 20 kilohertz, and we're down to about 3.5%. Roll this up to 50 kilohertz, and we're down to about 7% error. And if we bring it up to 100 kilohertz, we're down by about 13% error there. So as you increase in frequency, there's definitely a significant error involved. Now, these errors at higher frequencies are primarily due to the limited slew rate of the op-amp. So you can shell out more money and get a higher slew rate op-amp, but you can also realize improved frequency response by replacing the op-amp with a comparator. So this is configured such that the comparator's negative input terminal is tied to the capacitor. So the capacitor is its reference voltage here, and whenever the input voltage goes above the capacitor's voltage, it's going to go high, and it's going to start charging this capacitor until, of course, the capacitor reaches the same voltage level as its input voltage, at which point the two inputs to the comparator will be equal and the comparator will turn off. So it's a very simple configuration, but the advantage is that the comparator is designed to have very fast rising and falling times compared to a typical op-amp. So you can use a cheaper, less expensive comparator in order to achieve higher frequency response and less error at higher input frequencies than you could get with a less expensive op-amp. Now, for practical implementations, you'll probably want to add some input protection in front of the comparator, just to protect against any negative input voltages that might arrive on your input. I also like to tie the comparator's negative input terminal to the output of the op-amp, so that any errors in our op-amp buffer here are accounted for, although in this case, the error introduced by this op-amp relative to the error in the total circuit is going to be pretty minimal, so that's definitely not a requirement. And I also like to add a second resistor here, just so that I can individually control how quickly the capacitor charges by adjusting this resistor value, as well as how quickly it drains off by adjusting this second resistor value. So I've got the circuit built up on the bench here, and we can put it through its paces. I'm currently giving it a 1 kilohertz 2 volt peak-to-peak input signal, just like we saw in the previous circuit. And again, at 1 kilohertz, we get pretty accurate response here, 1.01 volts according to the oscilloscope's multimeter here. And if I roll the frequency up to, say, 10 kilohertz, you can see that same accuracy there. If we roll it up to 20 kilohertz, 30 kilohertz, 50 kilohertz, it's still tracking pretty well. Now, as we approach 100 kilohertz, it does start to drop a bit here, but 995 millivolts out of 1 volt, that's still well within a 1% error. So definitely performing much better than the previous circuit for very little extra cost and complexity. So I took some more accurate measurements of this circuit with my bench multimeter at 1 kilohertz and 100 kilohertz. And at both of those frequencies, I tested it at 2 volts peak to peak and 500 millivolts peak to peak. And you can see that it's pretty darn accurate. It's well within 2% across that range. So, for a simple circuit with, no precision components and just jelly bean parts, that's pretty darn good. Now, in some cases, you would really like the peak detector circuit to hold that peak voltage that it sees pretty much indefinitely. And unfortunately, when you're using a capacitor to hold the voltage, you can't really do that. You can make it work pretty well, but you're always going to have some current leakage through the diode as well as through your buffer amplifier. And there are some circuit tricks that you can do to minimize these effects, but you can never really get completely rid of them because you never have a perfect diode or a perfect amplifier. So there's always going to be some degradation over time of the voltage stored on this capacitor. So to fix that, really the only solution is to get rid of the capacitor. So in this circuit, you can see that the input signal is supplied to the same comparator. The output is buffered by the same op amp here, and the output is again fed back in as a reference voltage to the comparator, but the capacitor has been replaced by a digital potentiometer, an AD5220. Now the 5220 has a very simple input protocol. It's just a up-down input. So when the up-down pin is pulled high, as I have it here, whenever the input clock makes a high to low transition, this wiper is going to be moved further up. And so we will see a larger voltage output here, since this is just a voltage divider between VCC and ground. So the comparator is configured as an inverting comparator, such that when the input voltage is higher than the output voltage here, he's going to go low, and that's going to assert the chip select input. So the clock is then going to start moving the potentiometer wiper up further and further until the output just exceeds the input, and then this output is going to go high. And that will pull the chip select line high, basically disabling the clock input. So clock input is ignored whenever the chip select line is high. So we have a peak detector circuit here with zero droop because there's no capacitor to drain off. The output voltage is going to be held at whatever the maximum peak input voltage to the circuit is since power on. And it'll hold it there indefinitely, or at least until you remove power. So you do need a clock input to this circuit. However, since the LM393 is a dual comparator, you can just use the second comparator as a relaxation oscillator. And since the hold time of the peak voltage is indefinite, you probably also want to implement a reset switch here, so you can reset it to 0. And another thing to keep in mind for a practical implementation is that this AD5220 starts up with the wiper in mid position at power on. So you'd also want some automatic reset assertion at initial power on, just to make sure you pull this all the way low at initial power up. But that can be implemented with a couple of transistors, so not really a big deal. And so you have a fairly simple zero droop peak detector circuit. And this circuit works quite nicely. It will track the peak voltage and hold it there indefinitely, at least, of course, until I hit the reset button. But you'll notice there is a bit more error in this circuit than there was in the previous circuit we looked at, and that's primarily due in this case to the limited number of steps in the AD5220 digital pot. It only has 128 steps, and it's a 10 kilo ohm pot. So if you had a smaller value pot or a digital pot with a higher number of steps, you'd get more resolution and better accuracy. And of course, there's no reason we can't combine the two circuits together. I have the more accurate analog peak detector here being fed the input signal, and I'm monitoring its output on channel 1 of my scope, but I'm also feeding its output into the peak detector with the digital potentiometer, which gives us the zero droop output, and I'm monitoring that with channel 2 on the scope. So we can see right here that channel 1, which tells us the current peak value of the input signal, is currently sitting here right about 1 volt, since I have a 2 volt peak-to-peak input. And of course, if I increase my input signal, the output from the 0 Droop peak detector stays up at the maximum peak value, whereas the output from the analog peak detector simply tracks the current input waveform. And of course, these are just 2 of many different types of peak detector circuits that you'll find. So if you enjoyed this video, I highly recommend that you check out the references and suggested reading links in the blog post, which I'll link in the video description. And as always, be sure to leave any questions, suggestions, or corrections in the comment section below. Thanks for watching.